Hello everyone. So in the today's lecture we are going to see a new point from the radiation chemistry, and it is very important point, the radiolysis of water. And we know that the meaning of the radiolysis. So lysis means breakdown and radio means the radiations. So we will start with our today's discussion. The major products of the water radiolysis are the free radicals. So, the free radicals will be like H radical, then the electrons will be there. These electrons will be hydrated electrons or the aqueous electrons. Then OH radicals will be generated, H radical O2, H2O plus, S3O plus, H plus, OH plus, and some other molecular products like H2 and H2O2. So, during the radiolysis of water, all these products will be formed, and in the presence of air or the dissolved oxygen in the water, that affects the final yield of the products. So, simply air or the oxygen that will affect on the final yield of the products. So, these are the products of the radiolysis of water. So, we will see the 6 to 7 steps which are involved in the radiolysis. So, first process is the mean LET in water radiolysis. So, LET is a linear energy transfer value. So, this value varies with the nature of the radiation and the energy of the radiations. As we know, there are the alpha, beta and the gamma radiations are present, although there are the X-ray radiations. So, LET in water is low for the gamma photons and the higher energy electrons. As we know, the gamma photons are of the higher energy and some electrons are also of the higher energy. That's why the LET for the higher energy containing particles or the radiations, LET is lower, and it increases with the mass in the case of the particle radiation. So, here is the LET given for the gamma radiations, electrons, then the lower energy electrons, then protons, deuterium, alpha particle and so on. So, we will see the LET values that increases with the increase in the mass of the particle. So, as we know, the gamma radiation is of the higher energy, and we have told that the gamma radiation or the higher energy containing particle, its energy or the LET value is low. So, LET of the gamma is much less than the higher energy electron, then this is less than the lower energy electrons, then it is less than the protons, then it is less than the deuterium, it is less than the alpha particle, it is less than the heavy ions, and it is less than the fission fragments. So, simply as mass is going to increase, the LET will be increasing, and as mass is going to decrease, the LET will be decreasing, or there is a relation, the higher energy particles or the radiations are there, LET will be less. So, the log of LET will drops roughly linearly with the log of energy of the electrons. So, there is an inverse relation, and an LET of 100 kilo electron volt divided by micrometer for electron of energy 0.1 MeV drops to 0.1 kilo electron volt micrometer inverse for electron of energy 1 mega electron volt. So, the LET of a electron whose energy is 100 kilo electron volt. So, when the LET of the 100 kilo electron volt per micrometer of the electron, its energy is a 0.1 MeV, and that will drop when the electron is of 0.1 kilo electron volt per micrometer and its energy will be 1 MeV. So, this is the first point. We will see the next point, that is ionic products. So, the ionic products, here the following are considered as the initial reactants for the radiolysis process. So the gamma or the electrons of the higher energy that will interact with the water molecules, and there is a further formation of the products. So here are the reactions which are given, that reactions of the radiolysis of water, and this point is much important. So here are the reactions. First one is gamma plus water, and here the wavy arrow shows the radiations. So simply radiation interacts with the water and there is a formation of a H2O star. Means water absorbs energy from the gamma ray photon, it goes to the excited state. So this star or the asterisk shows the higher energy of that water molecule. And when the water molecule comes to the ground state, it will emit one electron. So water become positive. So H2O plus electron. This is the first reaction. Then again, when there are the higher energy electrons in the system present, then electron will interact with water. Then there is a formation of the H2O star, and that electron will be as it is. Only energy of the H2O due to the collision of electron and water molecule, that will be increased. So H2O star is there. And when that H2O star or the higher excited species comes to the ground state, it again emits one electron. And water molecule becomes a positive. So initial electron bombarded and the final electron ejected. So by adding 2 electrons, we will get twice electrons. So this is the second reaction. Same way there are the third, fourth, fifth and sixth reactions are there. Again, when electron interacts with water, certain final products will be formed, like the H plus, OH plus twice electrons. It gives H2O plus twice electrons. Then again, when water interacts with electron, there is a formation of OH plus H plus twice electron. Then there is a formation of H2O plus twice electrons. So here in the all cases, the final products are the similar. Then again, in the fifth reaction, electron plus water, there is a formation of O plus H2 plus twice electrons. And lastly, when H2O plus and the water molecule interacts, there is a formation of HCO plus and the OH. So all this reaction shows when the water molecule interacts with the higher energy particles or the radiations like gamma radiation and the electron, they will form the products or the ionic products, because each and every product has some charge. It will be either positive or negative. Okay, so this is the ionic products. Now the formation of negative ions by electron attachment is negligible, and electrons prefer to recombine with the positive ions for the neutralization or to get solvated during the relaxation time of water dipoles. Wise 10 raised to minus 11 second, that time is required for the formation of the water dipoles or the relaxation time of the water dipoles. So the equation is here, electron plus water, they interact and there is a formation of the solvated electron, that is the electron aqueous. And the ionic products listed above are detected by a mass spectrometer in the radiolysis of water vapor. So all these products that will be identified by or detected by the mass spectrometer in the radiolysis process. Then we will see the free radical products. So as we have seen, the ionic products are formed due to the interaction of the gamma particles or the gamma radiations and the electrons with the water molecule. Same way we will now see the free radicals products, and here again water will interact with the electron and there is a formation of the certain free radicals. So we will see how that will be formed. So the ionic products have all short lives. As we know, the positive ion or the negative ion or the species which is present in the excited state, it will try to come into the ground state and try to attain stability. So simply the ionic products have all short lives, and especially it is in the excited state. They recombine to yield the free radicals. So we will see the first formation of the radical. H2O plus electron, it gives H plus OH radical. So here the OH radical, this is the free radical formation occur due to the interaction of these two. Now we will see the next. So H plus plus H2O plus electron, and these are the final products which we have taken from here. So H plus plus OH plus twice electron, this is the final product here. Then again H2O star plus electron is there, OH plus H plus twice electron, O plus H2 plus twice electron, H3O plus OH. So all these are the products which are present in our system only. So that's why each and every ion tries to attain stability, and due to the interactions of that ions, there is a formation of the new charged particles. So here the H2O plus electron recombines to form the H plus OH radical. Then nextly H plus water molecule plus electron, they interact and there is a formation of the H3O plus electron. And from that H3O plus, when there is a heterolytic fission, it will forms the twice H radical plus OH radical. Then again the third reaction is here. OH plus water plus electron, it gives H radical plus twice OH radical. So here the OH radical, then the twice H radical, OH radical, H radical and twice OH radical. All these are the free radical products formed due to the interaction of the ionic products. Then in the presence of dissolved air or oxygen, per hydroxyl radical, it forms the HO2 radical, that is a per hydroxyl radical. So simply in the presence of the air or the oxygen, the per hydroxyl radical will be generated, that is H radical O2. So how that will be formed? So H radical plus O2 from the air, they recombines and there is a formation of HO2 radical, that is a per hydroxyl radical. So this is all about the free radical formation. Now we will see how the hydrated electrons will be formed. So the aqueous electron, it gives the H plus OH minus aqueous, and this reaction follows the first order kinetics. Here only aqueous electron, it gives H plus OH minus aqueous. So K is a rate constant, and for the hydrated electrons that will be 10⁻⁹ to 10⁻+10 per molar per second. And here is an example given by which the aqueous electrons will be generated. When we take the sodium and it will come in contact with water, it forms the electron aqueous and there is a formation of the Na plus, that is a aqueous sodium. So this is all about the hydrated electron formation. Now we will see the fifth point, molecular products due to the radical interaction. So see here, radicals are highly reactive as we know, because each radical tries to join with another radical and there is a neutralization of them. So initiate series of reactions with dissolved solids or they recombine amongst themselves. So as H radical and the H radical present in the system, there is a recombination, there is a formation of bond. So they will recombine amongst themselves, or there is a formation of the stable molecular products will occur. So we will see how that radical interaction will occur and there is a formation of the molecules. So the final products will be called as a molecular products. So H radical plus OH radical, there is a formation of the water. Here H radical and the OH radical both will combine and there is a formation of a bond, that's why water molecule will be formed. Then when H radical and the H radical will combine, there is a formation of H2. When OH radical and the OH radical will combine, formation of the H2O2. When OH radical plus O2H radical, then this two combines to form the products water and the O2. And the last reaction is here, O2H radical plus O2H radical. Here is the formation of the H2O2 and oxygen, that is O2. So simply by recombining the free radicals, we will form the molecular products by this way. Then we will see the sixth point, that is a chain reactions or the molecule radical interaction. So under the favorable conditions, molecule and the radical will interact, and due to that there is a chain reaction we will observe. So see how molecule and the radical will interact. So just take the radical and one molecule is here. So H is a radical and H2O2 is a molecule. When they interact, there is a formation of OH radical plus water. So here H2O2 will undergo the homolytic fission. There is a formation of OH radical and the OH radical. One OH radical will combine with the H radical. There is a formation of water and the remaining will be as it is. So this is the OH radical. Then this OH radical will participate in the next reaction, again OH radical plus H2. Then again H will undergo the homolytic fission, that is H radical and H radical. That is twice H radicals are there. One H radical will recombine with the OH radical and there is a formation of water, and the another H radical will remain as it is. So here is a chain reaction generated and it leads to a high yield of the radiolytic products. Now we will see the seventh point, that is a distribution of PRP of the water. So PRP means primary radiolytic products. So here, because of the 1000-fold higher linear energy transfer in the liquid water compound to water vapor, the spurs will be closer along the radiation track, permitting a greater interaction amongst the primary radiolytic products. So water will give H2O plus electron. So here the tracks and the pulse are there, and the energy will get distributed. Then we will see the free radicals in the water radiolysis. So as we know, the scavenging of the free radicals. Here deuterium scavenges both the H radical and the OH radical. Thus H radical plus D2, it gives the D radical plus HD. As I have told, the D2 will get homolytically fission, that is a D radical, and the D radical, that is twice D radicals. One D radical will combine with the H radical and there is a formation of the HD and the D radical. Then again when we have the OH radical in the system and we have the deuterium, that is D2. So just OH radical and one D radical will combine to form the HOD and the another D radical will be as it is. Then when this 2D radical and D radical will combine to form the D2 and the wall of the third body. So here is the G, that is very important. So G, number of molecules initially dissociated, we have to find out. So here the dissociation of the D2 will occur, then the dissociation of the HD will occur, dissociation of the water will occur. So here the yield is given, or the dissociation of the H and OH, that will given here. GH plus DOH is equal to 4 and GH is equal to GOH, it is equal to 11.7. So this is the number of molecules initially dissociated, that value is given here for H and OH. Now we will see the radiolysis of the Friquet dosimeter solution. So for that we have to prepare the solution. So 10 raised to minus 3 molar FeSO4, that will be taken in the 0.4 molar H2SO4 solution in the presence of the air. So 10 raised to minus 3 molar FeSO4, that solution is taken in the 0.4 molar H2SO4 in the presence of air, and the quantitatively reproducible oxidation of the Fe2 plus to Fe3 plus on the radiolysis is explained on the simplified mechanism. So as in the last lecture we have seen how Fe2 plus will get converted into Fe3 plus and how spectrophotometrically we have determined the wavelength and the amount of the Fe3 plus which is formed. So here is the equation which included in the Friquet dosimetry. So Fe2 plus plus OH radical, it gives Fe3 plus OH minus. So we have to measure this. Then Fe2 plus H2O2, it gives Fe3 plus OH radical plus OH minus. And next reaction is Fe2 plus HO2 radical, it gives Fe3 plus HO2 minus, and H radical is here. Then the HO2 On oxygen there is a minus charge, on the hydrogen there is a radical, and when it combines with the H plus there is a formation of the H2O2. So in the Fricke dosimetry, at the left side there is a Fe2 plus, at the right side there is a Fe3 plus. So we have to find out the oxidation rate of the Fe2 plus to Fe3 plus on the spectrophotometer, and by this way the radiolysis of the Fricke dosimetric solution will be observed. And the HO2 radical needed in the equation 3, this one, is obtained by the reaction H radical plus O2, and this oxygen is dissolved oxygen and it gives H radical O2, and the yield of the final product Fe3 plus is related to the radical and the molecular yields by the expression GFE3 plus present in the air. It is equal to twice G H2O2 plus thrice G of H plus G of OH. So the final value of the GFE3 plus or the molecular dissociation, that will be 15.6 for the Fe3 plus in the Fricke dosimetry.